Hey everyone. In the next two chapters, we are going to be talking about really our first functional group. And as we move forward, we'll go through this process numerous times. We'll talk about a functional group, we'll learn about its structure, its naming, its reactions, and all of those things. So the first functional group we're going to talk about are the alkenes. And so alkenes are molecules that have carbon-carbon double bonds. We're going to split this into two chapters this time because we are going to go over some review as well. So we're going to start off this chapter in this first lecture just reviewing the structure of alkenes and then going through and talking about how to name them. And there's going to be some discussion of stereoisomers. We talked a little bit about these before, but we got a new system to name some stereoisomers of alkenes. So after we do this introduction, we're going to step back and talk about reaction energies. So in order to understand reactions, we want to know how the electrons move, but we also want to know something about the thermodynamics and the kinetics of the reaction. So we'll spend the second and third videos talking about these types of energies. The second one will talk mostly about thermodynamics, and then the third one will talk about kinetics, so reaction rates. Before we get into the real structures of alkenes, let's discuss molecular formulas. Alright, so we've already talked about formulas of alkanes, like this one on the left. So really, to come up with a formula here, all we need to know is the number of carbons, right? So we have 1, 2, 3, 4, 5, 6, 7, 8 carbons, right? So can we come up with a number of hydrogens without having to go through and count all of the hydrogens that would be attached to those carbons? Yeah, we can, because we know that for alkanes, there's a generic formula that's for Cn, and for every carbon, there's 2n plus 2 hydrogens. Right? So for 8 carbons, 8 times 2 is 16, plus 2, we would have 18 hydrogens. All right? So what happens if we make a cycloalkane and we make a ring? Right? So if this one also has C8, but how many hydrogens are we going to have in this structure? Still 2n plus 2? No, we're going to have, because of the ring, we have to remove 2 hydrogens. So the formula of this compound is going to be CnH2n. So really we have to, if we went from this structure to this one, or from this type of structure to this one, we'd have to lose 2 hydrogens. And this loss of 2 hydrogens equals what we call an unsaturation. Okay, so if we have an unsaturation, it means that we have less than the maximum number of hydrogens that we could for that number of carbons. So a saturated compound like this one over here, we have the maximum number of hydrogens. Alright, so we fill this in, we'd have H16. Alright, so what if we have an alkene instead of a cycloalkane? So this has the same general carbon framework as the first structure. So we have C8. How many H's is this going to have? This likewise is going to have H2n, or 16. So an unsaturation can come from either a ring, or a pi bond. Alright, so unsaturations, oftentimes we talk about them in terms of alkenes, right? You've heard about saturated and unsaturated fats, and unsaturated fats have double bonds in them, and saturated fats don't. Alright, so what if we drew one more structure here? Let's see if we can figure out how many unsaturations it would have. So I'm going to do this one right here. Alright, so this one has a triple bond. So I'm going to use this way to draw triple bonds oftentimes, and just to point this out that these positions here, where the triple bond ends and a single bond begins, there's carbons at these positions. All right? So an alkyne has 2 pi bonds, right? So this has 2 unsaturations. We have the ring. This is 1 unsaturation. So this molecule would have a total of 3 unsaturations. Okay, so if we just tried to figure out its formula, let's see, we got 6 carbons in the ring, 7, 8, 9, 10, 11. This would be C11. If it was saturated, we would have 2 times 11, 22, plus 2 is 24. Right, so we have 3 unsaturations though, so for each of those we lose 2. So 24 goes back to 22, goes back to 20, goes back to 18. Alright, so we could figure out the number of hydrogens just based upon the unsaturations. Alright, let's just look at one more. Okay, what about this? Alright, so we see that it has a ring and a pi bond, so this has 2 unsaturations. Alright, so 6, 7, 8, this would be C8. H18 would be saturated, but it misses 2, 16, 2 more, 14, so this is H14. Let's just do one more. Let's stick it in here. We'll run into these a lot later on. What if we had a benzene ring? How many unsaturations does a benzene ring have? Alright, well it has a ring, that's 1. And we can see 3 pi bonds. Each one is an unsaturation. So a benzene ring has 4 unsaturations. Alright? Alright, so now let's go on and talk or remind ourselves the structures of alkenes. So remember, when we form a carbon-carbon double bond, that in order to do that, the carbon here, right, needs to have 3 equal bonds. 3 bonds, 1 for the carbon and 2 for the hydrogens to start off. And those are made up of sigma bonds. Right, because we need 3 of them, then we need those carbons to be sp2 hybridized. And we notice here in orange, it's just showing the big lobe of each of those sp2 hybridized orbitals. One of them is being used to make the bond between the carbons, and 2 of them are being used to overlap with s orbitals of those hydrogens. So this is the sigma framework of this molecule. So when we have sp2, then we have a remaining p orbital on each of those carbons. And remember that those p orbitals can overlap side to side like this, and this is called the pi bond. Right? Remember that the pi bond can only form when those 2 p orbitals are in the same plane as one another. All right? That puts the 4 hydrogens and carbons all in one plane. So this is a plane right here. Okay? So remember from this then that a carbon-carbon double bond equals 1 sigma bond plus 1 pi bond. All right? So that ends up having some kinds of structural implications as well. So think about the situation. What would happen if we rotated one of these carbons relative to the other one? Right? So if we tried to twist this one sideways, what would happen to the p orbital? So if we twisted it, it would twist that p orbital as well, And if those p orbitals aren't lined up, then they can't form a bond. So if we rotated around that carbon, it would break the pi bond. Okay, so rotation around the carbon-carbon double bond would break the pi bond. All right, so this can happen, but it takes a lot of energy to do that. So under normal conditions, pi bonds do not rotate. Pi bonds do not rotate. All right, and this leads to the possibility of stereoisomers. And I know I introduced this earlier, but let's look at it again. So if we have a molecule like this, so 4 carbons, just to give you a little preview of our naming, this would be, so butane, right, is 4 carbons. It has a double bond, so it's ene, so this is a butene. And we number it from one end to the other, like we normally do. The double bond starts at the 2 position, so this would be called 2-butene. All right? But if we want to draw this structure, let's just start with the carbon-carbon double bond in the middle. And on one end, we have a hydrogen and a methyl group, right? Hydrogen and methyl. But when we go to put the other hydrogen and methyl on the other end, we have 2 possibilities. Right? We can either put the methyl group over here, or we could redraw this. We'll keep one side the same, like this. And we could put the methyl group down here and the hydrogen up here. And because there's no rotation around that pi bond, this kind of equilibrium does not happen. All right, so these are 2 different molecules. They would in fact be stereoisomers. Okay, because they have the same connectivity of atoms. They're both still 2-butene. But they're different from one another. Different because of the 3-dimensional orientation of the groups. All right, so remember how we name these. If we make an axis down the carbon-carbon double bond, if we see these 2 methyl groups, and they're on opposite sides of that axis, we call this trans. It's opposite. And alternatively, if we make this axis and these 2 methyl groups are on the same side, then this is called cis. Alright, so we usually use trans and cis just when we have situations like this. We have an alkene in the middle of some carbon chain. Each end of the alkene, so this carbon, has a carbon and an H. And this end has a carbon and an H as well. Alright, so let's look more in depth at some naming. We'll look at additional examples here. Okay, so here's the rules. Like we always do, we're going to name the longest chain of carbons, but in this case, because now we have this functional group, this alkene, and this alkene is going to take priority over anything that we've seen up to now, we're going to make sure that the longest chain, we're going to name the longest chain that includes the functional group. All right? And we're going to use ene to indicate that there's a double bond. So let's just start into this first one. So let's pick the longest chain, or a longest chain that includes the alkene. Could be this one here. And then we're going to number this chain to give the alkene, the double bond, the lowest possible number. Even if there's some other substituents on there that could have a lower number, we're going to give that alkene the lowest number because it takes priority. Okay, so we're going to number from here. So in this case, the alkene is between positions 2 and 3. All right, and we're going to put a number out in front of the alkene name to indicate the first carbon of the alkene. So this is 6, right? So if we started out with the alkane, we're going to cross out the A and E, and we're going to make the E and E. So that tells us there's a double bond. Now the double bond starts at position 2, so this is a 2-hexene. All right, we have 2 substituents on here. Right, we have a methyl here and a chloro here. So we're just going to list these in alphabetical order, just like we always have. All right, so we're going to list the chloro first. We're going to fit this up here. We're going to have 5 chloro, right? And then the methyl's at 2 methyl 2-hexene. All right? Okay, let's do one more here. So here we're going to find the longest chain, but remember that longest chain has to include the alkene. So instead of numbering the absolute longest chain over here, we're going to pick this one as the longest chain because it includes the alkene, the high priority functional group. All right, and then we're going to number this to give the alkene the lowest number. So we're going to start here, 1, 2, 3, 4, 5, 6, 7. And so this is going to be a heptene, and the double bond is at the 1 position. All right, so we have to make sure even though it's at 1, we have to put the 1 there because that double bond could be at many different places along the heptene. All right, so then we have 2 substituents as well. We have a methyl here and an ethyl over here. All right, so we're going to have 2 ethyl. All right, ethyl comes before methyl in the alphabet. 5 methyl 1 heptene. All right, so let's do just a couple more. All right, so let's look at this next one. So the longest chain, so this ether doesn't matter. It's just going to be named, remember, as a substituent. So here's our longest chain. 1, 2, 3, 4, 5, 6, 7, 8. So this is an octene. All right, and the double bond is at the 3 position. 1, 2, 3, 4, 5, 6, 7, 8. So a 3 octene. All right. Then we have 1 substituent. This one here. Remember what that's called? It has a methyl and an oxy. This is a methoxy. Right, and it's at the 6th position. 6 methoxy 3 octene. All right, so in this case, is there another compound that could have the same name? Well, it turns out there is, right? Because we could have a stereoisomer that would have that same name, right? So we've got to designate which of these 2 stereoisomers we have, right? So in the bottom one that we were naming, if we look at the 2 alkyl groups on the double bond, they're across. So this one is trans. And the upper one, these 2 are on the same side. So this one would just be cis 6-methyl 3 octene. Okay? All right, let's do another one. Alright, so this one, the longest chain, is like this. Number to give alkene the lowest number. 2, 3, 4, 5, 6, 7. Alright, so this is a heptene, a 3-heptene. Alright, we've got two substituents, got a bromo and a methyl. So we got a 7 bromo, 6 methyl, 3 heptene. Notice that we're numbering, even though the heptene, the alkene, is at 3, and if we number it from the other way, the bromo would be at 1, we give that alkene the priority. Alright, anything else we got to put in here? Alright, so this one could have a stereoisomers as well, and so this is a cis, 7 bromo, 6 methyl, 3 heptene. Alright, if we have more than one alkene, this is called a diene. Alright, so again, we can number this for our longest chain. Alright, we could number like this, for example. We're going to give the first alkene the lowest number. So we're going to number from over here, 1, 2, 3, 4, 5, 6. So this is going to be called a hexadiene, with the double bonds at positions 1 and 3. So this is hexadiene, and it's a 1, 3 hexadiene. Now it has one substituent here, so it has an ethyl group, and that's going to be at position 4. 4 ethyl, 1, 3 hexadiene. Alright, so can this molecule have any stereoisomers, any cis or trans double bonds? Well, the test for this is if we take the groups at one end of the double bond and switch them. Right? So if we go, say, to position 4, we have this ethyl here, we have this ethyl here. So if we took those two groups off, we swapped places, would we get a stereoisomer? Well, if these two groups are the same, then the answer is no. We just get the same compound back. The other position that we have here as well is on this end we just have two H's. If we switch their places, it's just the same, so there is no cis or trans in this molecule. Okay. Alright, so the next one has an alkene in a ring. Alright, so we're just going to number it, or name this in the same way we did before. It's got 6 carbons. It would be a hexene, but it's in a ring, so it's a cyclohexene. Alright, in this cyclohexene, because the double bond takes priority, it's always going to be at position 1, so we don't have to put a number in front of this. Alright, so we're going to number it. We have two possible ways, though. We could number it from this side and number it clockwise. Or we could number it from this position and number it counterclockwise. Like that. So which way do you think we should count it? Alright, so the double bond is in position 1 and 2 either way, right? So that's essentially a tie. So we're going to look at the substituent and we're going to give it the lowest possible number. So we're going to number it as in red, right? And so this would be a 3-methyl cyclohexene. Alright, so let's look at the last one here. Okay, so we get a 5-carbon cycloalkene. So that would be cyclopentene. All right, no number needed. And we're going to number this like we did the last one to give the first substituent the lowest possible number. So we're going to number it from here because that puts the methyl group at position 1, even though the chlorine ends up being at position 5. We're going to give that first substituent the lowest possible number. So this one is going to be 5-chloro 1-methyl cyclopentene. All right, so notice, okay, that in a cycloalkene, we're always, in these types of ring systems, these sides, we're going to always have a cis ring, right? Because the trans would just put too much strain. Okay, so we cannot have trans, no trans in ring until we have 8 carbons in the ring or greater than equal to 8 carbons. All right, so if we had cyclooctene, that's the first place where we can start to have a trans double bond in the ring. Okay, so we're going to look at another system to describe our stereoisomers. Okay, so like I said before, cis and trans is usually used when we have 2 groups like this on each end of the double bond, right? We have 2 groups and we have 2 hydrogens. And here we could see that those are on the opposite sides of the axis of the alkene, so this is trans. All right, so but the next one that I have, we have more substituents, right? So what would we call this? Would this be cis or trans? All right, are we going to look at the alkyl groups, the biggest alkyl groups? Are those going to be cis, or are we going to look at the bromine? So what's cis or what's trans, right? So cis and trans are terms that describe the relative positions of 2 groups. All right, and so in this case we have 4 groups, and so it really doesn't work well for that. So this is be what we'd call a tetra substituted alkene. Okay, so anything more complicated than the one on the left here, we're going to use this new system. And this new system is called the EZ system because it's so easy. All right, and this is going to won't be too tough for us. It's going to follow a system using ranking, and that ranking is the same type of ranking that we used when we gave R and S designations to chiral centers. All right, so let's look at 2 possibilities here. Okay, so we're going to have a carbon-carbon double bond, and on each end of the double bond, we're going to rank the 2 groups as either high or low. Okay, so on this one, we could have high and low, right? Then we're going to rank the other end, and let's just say that we have this high and low, right? The other possibility would maybe keep this side the same, right? But we switch the right end, high, low. All right, so these 2 would be stereoisomers of one another. So what we do in this case is we look, like we did before, along the axis of the double bond, and we're going to look at the 2 high rated groups. So high and high, these are on the same side, and so because this technique comes from German, we could say that they are on the same side. Right? So we're speaking German here, of course. And so we call this a Z alkene. All right? Actually, it stands for zusammen, which is actually on the same side, or same side in German. But this is a little trick to remember it. All right, so let's look at the other one. In this case, we have high-ranked group here, and we have high-ranked group here. These are on the opposite side, and so we call this E for entgegen. I don't have a clever saying for that side, though. Okay, Z is when they're on the same side, and E is when they're on opposite sides. Okay, so this is kind of the generic plan here. Now we just have to go through some examples where we actually do the ranking. All right, so let's look at these complicated alkenes here. All right, so we got to focus in on the alkene, right? So in this first one in the upper left, here's the alkene. So we're going to rank the two groups on one end, right? So which are these going to rank higher? So we could do what we did before. If we look at this carbon, we go out one position, it's both carbons, so it's a tie. So let's list what's attached to that carbon, right? So we have one carbon and two hydrogens, right? For this position, we have two carbons and one hydrogen, right? So if we compare these, right, the first one is carbon and carbon, and then we have carbon and hydrogen right here. So this side is high, and this side is low. All right, so let's go to the other end. All right, so then we're going to look at these two, right? We start here, carbon, carbon, tie. So which side is going to be higher? All right, so I think we can see quickly that this side is going to be high, and this side is going to be low, right? Because this carbon has one carbon and two hydrogens attached, and this one only has hydrogens. So in fact, the ranking of high to low happens at this position, even before we get to the bromine. Okay, so now let's look at the two highs. Right, so we have a high here, we have a high here, they're on the same side, the same side, and so this would be an Z double bond. All right? Okay, we're not going to name the whole thing. We could do that in most of these, but let's just look at the EZ designation at this point. So what we would do, though, is we would put this Z out in parentheses out in front of the name. Okay, so let's look at the one in the upper right. So how many of these double bonds could have an E or a Z? All right, only the middle one, right? Because this one here on the end has two hydrogens. If we switch those, we get the same thing back, right? So let's just draw in these all of the groups. So on the left side, we know that this is going to be high, right? It has a carbon. This one is only hydrogen. This one's low, right? On the right side, we go out to the first position here and here. Carbon and carbon, tie. Remember that when we rank a carbon-carbon double bond, if it has a double bond to another carbon, we treat it as if it's attached to two carbons, right? So we treat this as carbon-carbon hydrogen. This position has an oxygen and two hydrogens, right? So which one is high? So oxygen has a higher atomic number than carbon, so this side is high over here, this is low over here. The two high groups are on the same side, and so this is Z. All right, let's look at the lower left. Let's see how many of those alkenes can have E or Z. All right, so can this one? No, that one can't, because on this end, these two groups are the same, right? So only this position can. So let's rank the left side. So we're going to have this one is high, and this one is low, right? Because this one has a bromine and 2 hydrogens. This one has only hydrogens. And the other end, we're ranking, right? We're ranking this whole group versus the hydrogen, right? So this group is going to be high, and the hydrogen is going to be low, right? So these are on opposite sides of the alkene, and so this is an E double bond. All right, one more. Okay, we only have one molecule here as well that can have an E or Z, right? So let's rank the left side, right? This carbon here would be considered as being bonded to 2 carbons and a hydrogen. What about this position? Right? It's already bonded to 2 carbons, and it has that double bond, so that adds another carbon. So carbon, carbon, carbon. So that makes this side high, and this alkene is low. Let's look at the right side. We've got some fluorines and some bromines, so which one is going to rank higher? Okay, remember, take it one atom at a time. So we start here, carbon, carbon, right? Tie. So then we look at what's attached to that position. This position has 3 fluorines attached. All right. This position has a bromine, a carbon, and a hydrogen. Okay, so which one? 3 of a kind beats bromine high? Nope. Bromine, we go to that first atom. Bromine has a higher atomic number, and so that's high. This is low. High and high are across. So this one as well is an E alkene. All right, everybody get the feel for that? So in this video, we've learned something about unsaturations. We have learned how to name alkenes, and we learned this new system for naming and designating stereoisomers on alkenes. All right. The other thing that we should be able to do is the reverse of that. We didn't do an example of that, but we ought to be able to take a name and draw the structure.